Hi everyone, thank you for the opportunity to talk to you guys about some exciting innovation work that we have done back in Outshift by Cisco. We're going to talk in this session about forecasting Kafka lag with machine learning. To an intro about myself, I've been in the AI ML field for about 20 years. Currently working as principal engineer AI for Outshift by Cisco. So Outshift by Cisco is a team that focuses on building innovation in new areas that Cisco has not focused on before. And I'm also an author on LinkedIn Learning on AI, ML, and big data. More specifically, I've authored 2 courses on Apache Kafka, getting started and building scalable applications. In terms of agenda, we're going to look at the Kafka consumer lag problem, which I believe a lot of folks who have deployed Kafka in production and have been using it would have faced in real life, and why we need to forecast lag, what are the uses of forecasting lag, the current approaches to lag forecasting, and how we can use retrieval augmented generation to forecast a lag. We're going to discuss in detail what our approach to lag monitoring is and also look at some examples for real-time forecasting. So what is Kafka consumer lag? So Kafka consumer lag, typically a single topic has multiple consumer groups, and consumers consume data independently of the producers. Now, lag indicates the number of pending records that are not yet consumed by a consumer group, and I'm pretty sure everyone here would have been pretty aware of this part. Now, lag can happen by design, especially when you're having batch consumers, which wake up at given intervals and then consume all the pending records, or because the consumers are not able to keep up with the producers in terms of the data being produced. Lag directly impacts the latency of data processing pipelines, and hence when outcomes are actually achieved out of this data. And I believe, again, what happens when there is unplanned lag happens. So you got pending records that keeps increasing over time, slowly building up the backlog. And there are delays in achieving the desired application service levels because there is delays in processing records. And there is usually a business impact that results from that. For example, if you have a real-time threat alerting system that is using Kafka to publish and consume all the messages and logs, and there is delay in processing, it's going to lead to a delay in actual threat alerting and the threat actually becoming real. A real-time recommendation system may not provide recommendation in time, again leading to loss of business. And the most problematic thing is that restoring service level is very involved and it takes a lot of time, because typically you're working on trying to increase the capacity of the brokers or the consumers because you're not able to manage the load. And also the big headache of going through and resetting and setting the consumer offsets so that you can continue processing from where you want, or how do you offload all the pending records. So that this is a very involved process in getting the system back into shape. So the better option is if I know that a lag is going to happen, I can take action earlier. So if you look at how lag happens, some of the popular lag patterns that you'll see, we see 3 patterns here. The blue one is typically how a batch consumer lag would look like. The lag will keep increasing up because the consumer is not running, it's a batch consumer. And the moment the consumer wakes up, it consumes all the pending records and it'll be back to 0 and it is going to start again. So this kind of a sawtooth pattern is something you will see in a batch consumer. A continuous consumer that you see in green, at the very bottom, you see that there's hardly any lag. There's like 1 record, 2 record lag that is kind of being consumed immediately. So that's kind of having a flat lag there. A lagging consumer on the other side is like there is a slowly increasing lag over time. Even though the consumer is consuming it, it's not consuming at the speed it should, and the lag slowly increases over time, and it's going to hit a threshold when it's going to have a business impact. What are some of the trends that we observed when looking at customer lag across several instances and consumers and types of Kafka topics, is that each consumer group usually has a steady state consumption pattern. In terms of in normal operating times, it always has this pattern, whether it is a sawtooth pattern or a kind of a flat pattern. So you're able to see that it's a very steady pattern, and the steady pattern keeps repeating over time. So there's a repeating steady state pattern over time, and it usually keeps the lag closer to zero or a steady value all the time. And then when lag happens, if it is due to hard failures, they are usually easy to track, like the cluster went down or your database went down or something like that. It is a lot easier to track, but lag creep is not, because you're slowly seeing the numbers increasing. It will increase, come down, and you don't know if it is actually going to catch up or it's going to keep increasing ever. So this is usually happens when there is increasing load versus limited capacity. There are soft failures across system infrastructure, like your network becoming slow, your disk access becoming slow. And when lag happens, the biggest question is, will the consumer actually catch up? Are you going to catch up or are you going to not? And I believe a lot of you guys would have been in a situation where looking at the lag happening and you're wondering, is it going to catch up or should I take action? So that indeterminate state is where the predictions are going to come and help. So as we said, steady state and exception patterns do exist, which means it enables us to build machine learning models to take advantage of them. And patterns, but the patterns do vary based on individual consumer groups. Each consumer group will have a unique pattern to which we need to build our models against. So how do we forecast Kafka lag? Why forecast Kafka lag is so we know if the consumer group won't catch up eventually. So we know this ahead of time, and we can go ahead and take action. We can mitigate the problem, we can mitigate and possibly prevent the problem. So we want to forecast lag so that we know the problem is happening upfront, and then we can take action before it becomes too serious. And you have time to implement any corrective actions that you want to take. And it can also minimize your business impact. You could possibly mitigate the problem before your customers start noticing it, and avoid loss of revenue and trust. Now, how do you forecast lag? So this is kind of the concept that we wanted to build upon, is that when we look at the Kafka lag, it is essentially a sequence of numbers. And in that sequence of numbers is something that happens over time. And if you're making observations of Kafka lag every 5 minutes, 5 seconds, 10 minutes, however it is, you see a sequence of a time series kind of a pattern coming out. Now this pattern represents values over time. And for the purpose of forecasting, we observe these patterns over time, and we divide that into a key and a value. So the key is the first X points, like the first 6 points or the 60 points, and the value is the next 4 points or 40 points. So you can observe these patterns over time, and you can take that as your data set, split into these keys and values, and then the modeling would be, given a key, can I forecast the value? So it's kind of, when I'm given a key, can I say what the value for this key is going to look like for this specific consumer group? So in real time, at specified intervals, say every 1 minute or so, we can keep getting this last X data points, last X Kafka lag observations, and try to then predict what is the next X observations. And if we keep repeating this over time, we can easily see the pattern and see if it's a lag building up or not. The most important thing being, can I predict the value if I know the key? And for that, what are the approaches that are available today for lag forecasting? The first one is called ARIMA, or moving average computation. This is the classical time series modeling technique that has been there for quite some time. It is easy to implement. It can give good forecasts on patterns that are heavily repeating. But it has problems trying to handle nonlinear relationships or sudden shocks, which is what lag has. So it's got some strengths, it's got some weaknesses. This is what was classically used in most of the time series forecasting techniques today. You can have machine learning sequence models, like you can use a deep learning model to forecast the next pattern in the time series. So the same deep learning patterns like LSTM or even transformers, where you can predict, give it the part of the first sentence and predict what the next sentence is. You can do the same thing with numeric data also. And they can actually model complex patterns and relationships, especially the exception patterns. They model very well. The problem is they are very expensive to use, especially when you need to make predictions or lag every 5 seconds or every 10 seconds or so. A third option is to use a knowledge base of the previous pattern. So I can observe a Kafka topic over time and see that, collect these key value pairs over time. And then every time there is a problem happening, I can use the key to see what the value should be using the knowledge base that I've already collected. This is easy to manage. It has low cost for lookups. The problem is that I need to build up this prior pattern database for a given topic. Also, if some new pattern is happening in production, it cannot forecast. So each of these technique has some advantages and shortcomings. So this is where we get into the generative AI world and what we can do with it. And as you know, Gen AI is something that you're hearing all over the place, especially this year. And this has been applied to several use cases in machine learning. Now, the interesting thing is even forecasting sequences of numbers is a generation use case. Mostly people think Gen AI is all about text or images or videos. But generative AI is also generating the next sequence of numbers. So can we apply the generative AI techniques for forecasting Kafka lag? So generative AI models can be built to understand sequence patterns, and then you can use it to forecast into the future. And that's what we're trying to do here. And in that, we're going to adapt another technique that you popularly see today in generative AI world, which is retrieval augmented generation. So retrieval augmented generation is a generative AI technique for creating knowledge-based applications, example, like question answering applications. What it does is that it uses a combination of a knowledge base that stores information about a specific context and a deep learning model that can take the outputs of the knowledge base and then use it further for prediction. So it has a model as well as a knowledge base. It uses the combination of both to give you accurate domain-specific answers. So using a knowledge base, it constrains the output to a specific domain. So it's not going beyond the domain. But it also saves significant cost than just using your deep learning model all the time. Also, so there is a cost advantage as well as a domain advantage and they kind of complement each other to give you better predictions. So how are we going to use this in forecasting Kafka lag? So the technique that we developed for forecasting Kafka lag is to start with the pattern database. The pattern database essentially is built based on previously observed patterns for a given Kafka topic consumer. So we observe data over time, and for that we take the data, split them into key value pairs, and then create this pattern database of keys and values of all the past observed patterns. Then we also have estimation models. So these are deep learning models that are built. They are trained on previously observed pattern, but again, we are trying to train here on more generic data patterns. So the estimation models understand general purpose patterns much better. And we are using an ensemble of models. So it's not just one model. We have a collection of models. And every time we want to make a prediction, we let all the models make a prediction. And then we try to take the output of all the models and then see, are they in sync? They are not in sync. Are they convergent, divergent? And based on that, make a decision of whether to use the prediction or not. So what happens during prediction is you got the client. So in this case, a client could be somebody who's looking at Kafka lag. This is going to take the observed lag pattern as it happens. Like I'm going to be observing every 5 seconds or so. And then it is collecting the last X observed values. And it is going to keep sending this observed values to the system and keep collecting the predictions or forecasts. So there is a forecast engine in the middle to which this client sends. And this forecast engine uses both the pattern database and the estimation model. So it uses the pattern matching service first to see is there a matching pattern in the database, especially the key. I mean, it sees that there is a key, in fact, a very closely matched keys or set of keys. Then it tries to use just the pattern database to make a prediction, because this is like a repeating pattern, steady state pattern. You don't have to use a model for it. And most of the times when it is steady state, the pattern database will suffice your needs. Now, if the pattern database is not giving a good prediction, a high quality prediction, then it is going to go through the span estimation service to the estimation models. Here, what it is trying to do is, it is trying to have multiple models estimate what the lag pattern is going to be, and that can give you a bunch of patterns, and it's trying to see how convergent or divergent these patterns are, looking at its mean, its standard deviation, etc. And if there's a convergent result, it is going to give that back as a high quality prediction. If not, it is going to say, I still have a prediction, but it is a low quality prediction. So the clients always get a prediction qualified with a confidence level which says high, medium, or low. And as the client continues to use this, it's going to go and make predictions. So to kind of summarize, right? You got the pattern database that is built on the past observed data. It provides steady state lag patterns and exception patterns that are already observed previously, and usually sufficient to forecast lag when there are steady state operations. And when there is steady state operations, when this database is well built up, most of your predictions are going to come from the database, and it is very cheap. The ensemble of estimation models, it provides general patterns, especially those that are unknown so far for a given Kafka topic or given Kafka consumer. And it is only used when the pattern database doesn't have good matches. So the database doesn't have good matches for a specific consumer. I'm going to go to the models to give me an estimation of what the lag could look like. It is expensive, but helps to model unknown scenarios. And then you have the forecast engine. It is a smart engine that picks between what is coming out of the pattern database and the ensemble models, and then it tries to make a prediction on the quality. So it always goes to the pattern database first, then uses the ensemble models only when the pattern database does not return high quality results. And it uses heuristics and machine learning for making decisions. And then we add this and add AutoML for training. And what this essentially is that we continuously observe Kafka Lag for a consumer, for a given consumer group, and then you send it to the forecast engine to start building its database. So the pattern database gets built. The model also gets retrained or customized if it starts seeing anything new. And then the pattern database, and then the models are with the new patterns. When new patterns are observed, when drift is observed, the model also gets retrained, and it continues to adapt to the new data for the consumer group. So some real-time forecasting examples that we have a dashboard to build upon. So this is essentially a dashboard. What you see here is the blue line, the first part of the graph that you see. This is for a batch consumer. The blue line is essentially what is observed so far, and the green line is the predictions. So I'm going to just turn it on. So you see that slowly the graph starts moving to the left, because as each new point is observed, new lag point, data point is observed, it keeps getting predictions. And you see that the confidence flipping between medium and high, and the color keep changing based on how accurate the forecast engine thinks that the prediction is going to be. You also have a purple line in the middle, that is the trend line, that shows you what is the overall trend that is coming up, whether it is a flat line or up, or a line going up or going down. So even though this is a seesaw pattern, you see the trend line going straight, which gives you the confidence that the lag is keeping up. We don't have to worry about it. We also add a threshold line on the top, so that if the lag goes above that, it means that we need to worry about it. The second one is another one for a continuous consumer, where the lag is really flat, and you see the predictions also look flat into the future, so that this tells us that we don't again have to worry about anything here. And a third one you see is for a lagging consumer. How does a lagging consumer look like? Again, you see the observed values are slowly increasing, and the prediction is now showing it's going to really go up. The trend line is also showing that it's going to go up. So this is an example of this is an example of how it will be for a lagging consumer. So in this case, the trend lines are going up. So this is some kind of, I would say, research that we have done and built this model and the prediction system. And now we continue to build upon it to make this a product. How do you use this lag forecast? We set up thresholds based on expected consumer behavior. And then we could automate querying the system at periodic intervals to say, to periodically query at regular intervals to get the next set of predictions. And as we keep collecting these predictions, we keep looking at what the trend line looks like, and is it going to violate my threshold for lag in the future. We can keep looking at it. Again, we don't have to look at just one prediction, but we look at over time to see if the trend line is consistently should keep showing up, and then based on that, we can take action to either go look at increasing some debugging it or increasing some resource and stuff like that. And this also then can be used to trigger alerts or actions when the trend points to threshold violations in the future, like sending an alert, sending an email, things like that. And what kind of future work we are looking at? We're trying to add ARIMA-based models to have a third dimensional to the forecasting engine. So you have ARIMA, you got a machine learning model, and you have a knowledge base that together can work to give me better and accurate forecasts. And we're trying to build a Kafka plugin that you can plug into a Kafka cluster where you can observe Kafka Lag by consumer group and then publish that to the forecast engine, both for building the database and also for creating predictions. And of course, we're adding user interfaces for provisioning and analytics going forward. And then triggering mechanisms, either the triggers can go into a Kafka queue or send an email or call an endpoint. Those are also things that we are trying to build up. So that is pretty much what I have. Thank you.